Hi, ladies and gentlemen. I hope that your day is going well. Um, in an ideal world, you would be doing some demonstrations of Newton's first law of motion. You did a lesson about Newton's first law the other day, and ideally today we'd be doing some demonstrations that have to do with that. But today, video is going to have to suffice. That doesn't mean that at some point down the road that we won't do these demos in person, however. So don't get too disappointed there. Um, so, what I'd like you to start doing here is to take the piece of paper that you were given, and I'm going to ask you to do the fill in the blanks here. You're telling us what Newton's first law is. Go ahead and pause the video to fill that in. All right, so hopefully you have had a chance to fill in the blanks there. And of course, Newton's first law of motion states that objects at rest tend to stay at rest. Objects in motion tend to stay in, that's right, motion at a constant speed and in a straight line. That's really important. It's not just that they stay in motion. It's not just that they stay moving. It's that that motion is exactly the same as it was before. It is at a constant speed. It's in a a straight line. Unless it is acted on by an unbalanced force. Okay. And of course, this law is also known as the law of inertia. All right. So, ladies and gentlemen, we're going to take just a moment and take a look at a couple of your classmates doing the same demo that you watched Steve Spangler do just a few minutes ago. So, we will begin by taking a look at, let's go with this one here, and we're going to see Sophia. Uh,
Okay.
All right. So 3, 2, 1.
Wait.
All right. One false alarm. Okay.
I got it.
3, 2, 1.
Yes, I knew it. Oh, it cracked. It cracked.
The egg cracked.
All right. So.
Yeah, doesn't matter. I know it.
Yeah, I did see a crack there, but well done.
I would have been too scared.
Well done. All
My
right.
face is probably no chickens.
Okay, are we good?
That was very impressive. You can stop that.
all right. So, ladies and gentlemen, you saw there that Sophia was quite successful in her attempt to get the egg to fall into the glass. Now we're going to take a look at another example, maybe not quite so successful.
So theoretically, we've now seen one example of what happens. So our theory now is that the egg is going to fall into the water. Let's see if that holds true.
She's gonna
Don't.
Let's go.
Chanel, are you ready?
Yes.
Zach, I want a snack.
Do yours. Okay, let's write it down so Zach can hear the 3, 2, 1 very easily. There we go.
I'm sorry, I can't see.
Please give a hard smack.
1.
Zach, no!
Alright, that was the Zach.
All right. So in this particular case, Zach was not quite as successful as Sophia had been. But I think one of the important things to remember is that even when things don't go the way that we think they should, okay, it does not mean that Newton's law is still not at work. Any kind of motion that happens, Newton's first law, as well as his second and his third, which we'll learn about after break, but um, his laws are still at work even when things don't go as planned. So we'll talk here in just a moment about perhaps what it was that happened in this particular case. So we're going to take a look. We've got a still shot here from the Steve Spangler video. And so, of course, we've got a glass of water down here. Okay. We've also got a hand that is about to apply an unbalanced force to the edge of the pie pan. The pie pan is then going to slide across and apply an unbalanced force to the toilet paper roll. The toilet paper roll is then going to slide out, and so it might be thought that as the toilet paper roll brushes against the bottom of the egg, that the egg would go flying off as well. However, we know that this does not actually happen. All right, so instead, what does happen is that the egg falls straight into the glass. Why? Well, the egg doesn't go flying out to the right the same way the pie pan and the toilet paper roll do, because the egg has more inertia. Okay? It has more mass, and therefore its tendency to stay at rest when it is already at rest is much greater than the tendency of the pie pan or the toilet paper roll to stay at rest. So the egg wants to stay at rest. The brush of the toilet paper roll against the bottom of the egg is not enough force to overcome the inertia of the egg. The egg, for a brief moment in time, uh, does stay still, except for there's one little problem. As soon as the normal force, the upward force of the toilet paper roll, disappears on the bottom of the egg, now there is an unbalanced force being applied. That would be the force of gravity, causing that egg to fall down into the water. All right, so what I want you to do is to take out your paper once again, and actually we're going to switch over here, and I want you to take a look at this explanation I have here that uses scientific terms in the directions there. It gives you a list of some terms that you might want to include in a good explanation where you are describing something that happened and how it relates to Newton's first law. So for this one, we're going to go ahead and we're going to kind of copy this down so that you have an idea of what a pretty good explanation would look like. So for the egg drop, we're going to write an unbalanced force was applied to the pie pan by, we'll say Sophia's hand. Why not? Since she was a little more successful. This caused the pie plate to move and apply an unbalanced force to the toilet paper roll. This caused it to move. The egg, however, has more inertia than the pie plate or the paper roll, and so it is not moved by the force applied to the pie plate. However, once there is no normal force supporting the egg, the unbalanced force of gravity causes it to fall in the glass of water. Go ahead and pause the video so you can finish writing that down. All right, hopefully you've had a chance to pause and get that written down. I want to go back for just a moment and talk about the problem that we ended up having with Zach and his attempt, because I have to tell you, his technique was actually very good. Uh, Looking at it, he should have been successful. So I want to talk a little bit about why he wasn't, and yet how Newton's law was still in effect. The egg that Zach had up here, I realized as I was putting it on the toilet paper roll that there may have been a problem, but I chose not to fix it. I was like, oh, it'll probably be all right. The egg was pretty small, which meant that the egg sat down further inside the toilet paper roll instead of really resting on top of it, which means that when the toilet paper roll did move, there was more of friction between the toilet paper roll and the egg. So more of a force was applied to the egg, and it was enough force to overcome the inertia of the egg, and so the egg actually moved over a few inches before it dropped down. So Newton's laws were still in effect. Just didn't happen to be successful because our egg was a little bit too small. All right, we're going to take a look at one last demo. So let's take a look at this one.
Alright.
Shoot, there's not a word. She's still going.
Guys, stop talking. You need to count
3,
Let's go.
2,
Big W.
1.
Oh! Yeah!
Alright.
All right, so ladies and gents, I'm actually going to see if I can get back there a little bit and just, and all right, I'm going to kind of pause it here. And when I pause it, of course, it gets a little blurry, but I want to take a look at what is happening here in this demonstration. So this is a pretty classic demonstration of the tablecloth pull. I will tell you that up until the last like 2 years, I have only been successful probably 50% of the time or less. I've had a few plates and bowls get broken over the years. However, I've gotten a little bit better at it over the last couple of years. And uh, a lot of times, people will ask me, well, why don't you just use plastic so that they don't break? Well, there's actually a really good reason for that. This would be completely unsuccessful if we used plastic plates and bowls. Why? Plastic plates and bowls do not have nearly as much inertia as the heavy ceramic plates, bowls, glass, water in the glass. Okay, all of that makes this a success. Uh, so because the bowl, the plate, the glass of water have so much inertia, it would take a fairly large force to actually overcome their inertia and cause them to move. So even though there is friction between the tablecloth and the plate and bowl and things, it's not enough to overcome their inertia because they have so much mass. Now, the fork kind of flew up in the air a little bit. A knife moved some. They have much less mass, and therefore the inertia is not as great. All right, so let's just take one more look at it so that you can see which things moved and which things didn't. So I'll back this up a little bit.
She's still going.
I don't know. Guys, stop talking. Finish the count.
3,
Let's go.
2,
Big W.
1.
All right, so ladies and gentlemen, I have to admit that's kind of a fun thing to do. All right, I'd like you to take your paper back out. And this time I'm going to ask you to go down to the tablecloth, Paul. And I'm going to ask you to do your best at writing a scientific description using scientific terms, such as those mentioned in the directions, to explain what happened in the tablecloth pull that demonstrates Newton's first law. All right. You're going to go ahead and do that. Then you're going to put this paper into your binder. We're going to take another look at it when we get back from break and review Newton's first law real quickly before we move on to his second and third laws. Ladies and gentlemen, have a great day.